Okay, so now we can get really started. So put into the chat now, what are there some Greek mathematician names that you already know? And by this, I mean, there could be Greek mathematicians also, more modern, but like the ones from the BC time. So I see Pythagoras, Archimedes, Euclid. Those are the three most widely known names of the Greek mathematicians. Here's another Euclid, Pythagoras, Archimedes, Euclid, Pythagoras. Galileo is more modern. He's Italian. Plato was a philosopher. He actually did a lot in promoting math as a thing that was important to study. So Plato himself didn't do much math. In some of his dialogues, there are some mathematical things going on in them. They're not there. So he learned math for sure, but he wasn't. He didn't invent any math. Okay, so that's good that we know a few of the names, and those we are going to be studying some of these people and their discoveries. So in Greece, here's some names for you. The first name that we really have associated with inventing and developing geometry is someone named Thales, and that was in about 500 BC. Pythagoras was also around 500 BC. Euclid was a little later, 300 BC. Euclid wrote a book that's called the Elements. And the Elements, there are other books that were called the Elements. The Elements is what you called a book that had geometry theorems in them. So there were other people who wrote books that were called the Elements, but Euclid did such a good job at that book that the Elements is aside from the Bible, is the second most published book in the history of the world. And it was in continuous use as a textbook from 300 BC and until now. Like in the 1950s, in like a school, like some private school, classical education, they would use Euclid's Elements as their textbook. And the geometry that we learn, Euclid's Elements is sometimes called the 13 books of Euclid. But it's not really, each of those 13 things is more like a chapter of a big book. And the math that we learn in geometry class in school all comes from book 1, 3, 4, 5, I think, and 6. So in our basic geometry class, where you learn about triangles and parallelograms and things like that, that's all, book 1's all triangles. And 3 start dealing with quadrilaterals, parallelograms. 5 starts dealing with the circles. 6 deals with similar triangles. And then they start doing a lot of three-dimensional stuff. And then there's even a couple of books of what's now called number theory in the Elements. So it's not actually all geometry. Things like finding the greatest common divisor of two numbers is a thing that's put into Elements book 10. That algorithm is actually called Euclid's algorithm. Euclid himself is not considered to be like a great, mathematician. He's more of a someone who collected all the great math and organized it in a really logical fashion that endured for thousands of years. And he was a pretty great mathematician, because you can't write about this stuff, but he's not considered to be, he's more of a writer and a math teacher than someone who like invented so much original math.
Hey, Professor, is it
Yes.
fair to say most of what students would learn in a high school geometry class was actually kind of put together in ancient Greece? I mean, did they kind of really set the bar for the content?
Oh yeah, well, I think it's sort of the other, it's more like they did such a good job in the elements that people say, well, we got to study this thing. It's so like interesting. And then we still study it today.
Okay.
So as far as setting the bar, they made something that was so like popular,
Yeah.
that it's endured to this day. In my opinion, you could get that, you wouldn't like, I love it, but in my opinion, it doesn't really serve any real big purpose for us in modern times. And in that, there's various obscure theorems about a circle and two, like, is it really that important to our lives that if you have a circle and two lines, two chords intersect, that these things have to have the same product, A times B has to equal C times D? Like, how important is that to our everyday life? It's not important at all. But the proof of it is like really sophisticated and like clever. So back in the day, that's all there was to study. So you studied it, but we still study it today. I like it, but I just think it's overkill to make students in 2020 study these theorems. But go ahead, your question?
Yes, thank you.
Did you want to make a comment? You could disagree also, because a lot of people say, well, geometry, it trains the mind. You study a geometric proof that has like a logical sequence, and that helps you now when you're whatever job you are, you have to sequence your activities. You think sort of the way that a geometer thinks when they make a proof. There's actually not any evidence of that learning geometry helps you organize big projects that have nothing to do with geometry better. Nonetheless, it really is an interesting topic. I just could imagine a parallel universe. I wouldn't even be able to call it a parallel universe, so I wouldn't be so familiar with that word in that parallel universe, but where geometry died out as a thing that people really had to learn in school. There's other things they used to learn in school, like they learned spherical geometry, where you learn all these theorems about spheres, and that helped them with astronomy. And a lot of math was developed as a way to study astronomy. So there's all kinds of theorems about like triangle-like things that are formed on spheres that are totally foreign to us now. There's hundreds of theorems about spheres. It's called spherical trigonometry. It used to be a thing that we studied, but then they said, you know what? We don't really need spherical trigonometry anymore. So it's a thing that you can study. I have a great book that's called Heavenly Mathematics that taught me about spherical trigonometry and spherical geometry, but it's obsolete. And in my mind, so is Euclidean geometry. But it's an amazing thing that this Euclid's Elements blows your mind. If you're into that stuff, and if you're taking a history of math course, it's one of the most important books ever written.
But if you were an engineer designing a satellite that needs to be sent into geocentric orbit, I mean, wouldn't you need to understand some sort of spherical geometry?
Oh yeah, some people. Yeah, I mean, some people need to know it, but not so many. It's like saying someone might need to be able to play the Rachmaninoff concerto, Rock Concerto number 3. So therefore, we're going to force every single kid to take piano from the time they were in kindergarten, through 12th grade. So yes, some people need to know spherical trigonometry, but does everyone need to know it? No, I mean, I don't think so. Uh, and maybe 100 years from now, regular geometry will be considered obsolete, just like square root algorithm is considered obsolete now. It's funny that geometry survived and square root algorithm, did not. When I talk geometry, I don't mean just like, oh, in 8th grade, you learned the volume of a sphere was this. I'm talking about geometry, the one where you start with the most basic principles and slowly build up theorems that then get used to prove other theorems, that then get used to prove other theorems, until you have a body of 400 theorems about obscure things. For instance, I don't want to pick on this theorem because I love this theorem, but that in a circle, if you take two chords in a circle and intersect them, that the product of the two, that the product of the two of these two lengths will equal the product of those two lengths. It's a really clever thing, and it's surprising that that's true, and it's surprising that that you could prove such a thing. But it's not very important to prove it. You could get through life without ever knowing that fact. Anyone want to chime in on? You could totally disagree, because geometry for you might have been a very personal thing. You might have. I know people who say, oh, I really struggled with algebra, but when it came to geometry, I really thrived because I was so good with the triangles and the logic, and I didn't like all the numbers. Anyone have any feelings one way or another about geometry that they want to?
I
Yes,
was
Molly?
reading an article about someone who had dyslexia, and he was unable to learn algebra or other forms of mathematics, but he thrived in geometry.
Yeah. Yeah, well, geometry, I mean, I think it should be offered as a thing, but just like we don't make everybody take calculus, we shouldn't make everyone take. Actually, I think just to graduate in New York State, you don't need geometry. You just need to pass Algebra 1 Regents. So we don't really make everybody take it, but it's kind of understood that the next course after Algebra 1 is geometry. I saw Molly's hand up there also. Did you want to make observation?
Yeah, I was actually, it was similar to what I think it was John that just said. When I was younger, I had like visual processing issues. So I had some trouble with like just like the computational math that I learned in like elementary school and middle school. And when I got to high school and took geometry, it was like much more intuitive and really helped like spark my interest in math in general. Because I found I was able to like keep up with it a lot more. And so it made me more interested to go on, like when I had to take algebra 2 and pre-calc, those things. I think it was helpful in that way.
Great.
Yeah.
So yes. And oh yeah, so someone else wanted to say something, Grant?
Yeah. So I liken it to when we were doing the Chinese lesson and we had the geometric picture of what a square root is. That's much more clear about what a square root is than many of the other methods we try to teach people to solve these things. And so I think geometry is incredibly useful for actually building a conceptual knowledge of what these things are.
Very nice. It's the geometry you need for the understanding of the algebra things is small. In other words, having some geometry, some rectangles, but like most of geometry is some theorems that don't even help you visualize, something, like an algebra thing, like help you understand an algebra thing better. So in New York State, they used to have something called integrated. First, long ago, it was algebra, geometry, trigonometry. And then somewhere around 1984, they had something called integrated math, integrated 1, integrated 2, integrated 3. And they put geometry and algebra together into one course. Over a 3-year period, you built up both the geometry and the algebra. Integrated 1, 2, and sequential math 1, 2, and 3. These sequential maths, this curriculum for the regions, endured from like 1984 all the way up to like 2005. So for 20 years, it was sequential 1, 2, and 3, and it was very good. And it did include geometry in Algebra 1 somewhat, just to, some of what you need. It was a really good idea, and that's why it lasted for so many years. Well, in about 2005, they said, let's change it to Math A, Math B, and each one will be a year and a half long. And that was a disaster. That was a 5-year disaster because
Those were my
people
years.
took the regions
Sorry, Professor.
a year. How did you say that again, Crystal?
Those were my years, Math A and Math B. Oh God, they were horrible.
Well, you took Math A from one teacher the first year, and then you had a second teacher the next year for the other half, the other semester you needed. Math A, Math B is like, it's like, we don't talk about Bruno, we
Oh
don't
yeah,
talk about Math
definitely.
A, Math B. Sorry, Crystal, you had to endure.
It's
Math
all
A,
good. I'm
Math
still
B.
here though. I still like math.
Okay, good. Then they switched to back to algebra, geometry, trigonometry, and then they switched that these other things, Math A, Math B, these all lasted for like 2, 3, or 4 years, and currently they're in Common Core algebra, geometry, algebra 2. What will be next? I don't know, but sequential 1, 2, and 3 is like teachers look back on that. Any teacher who was teaching between 1985 and 2005, like longingly remembers sequential 1, 2, and 3. Beth says it was disappointing. Yes, Beth says so. You went through sequential 1, 2, and 3. Yeah, it was good. It really was good. I really get into like curriculum and what's a good curriculum and what's good topics and what makes a good test and what doesn't make a good test. Those things were just some kind of a perfection. Kind of like Euclid's Elements itself has endured for all these thousands of years because it's so well organized. Now, we're going to start doing some math now. And I have, let me go like this before I get to Bailly's Theorem. So let's start with Bailly's. One of the first geometric theorems that was like discovered is that the sum of the angles of a triangle adds up to 180 degrees. So and that's a thing they teach now to, like, I would say most fifth graders would know that just as like a fact. They're not proving it, but they know it as a fact, and they know if this is 70, and this is 60, they'd be able to figure out the third angle is 50 degrees. That's a thing they do. Fifth grade. It's like a trivia, what are the angles of a triangle add up to? You should know that back in those days, they did not have degrees yet as their unit of measuring angles. By Euclid's time, the unit of measurement for angles was the right angle. So you would say, 30 degrees, you would say 1/3 of a right angle. 45 degrees, you would say half of a right angle. So you would say angle A plus angle B plus angle C is equal to 2 right angles. 2/3 of a right angle, 60 degrees. It's pretty, so you couldn't get very refined calculations. And eventually, within, 200 years, by like 100 AD, they had degrees. They really needed degrees for astronomy. But the Greeks used the right angle, at least by Euclid's time, as their measurement. Now, let me see if I can bring this up. There are various software for studying geometry. One of the best ones is called GeoGebra. You type geogebra.org, start calculator. That's coming up kind of slow. I like geometry. And what this allows us to do is select, it's a drawing program. So I click on segments and I click on 2 points, I make a segment. Click on the first point and another point, make another segment. Now, if I go back to move, what's neat about this, unlike most drawing programs, it stretches the stuff around. And then I can join A and C together if I'm careful about it. And now I've made a nice, nice triangle. And then I can do stuff. I can measure the angles. You have to click on these. You click on the vertex second. You go in a clockwise fashion, otherwise it like measures like the outer part. And you can see as I change my vertices around, the angles change. So in this version, let's see, I'm not able to easily, maybe if I go like that, oh, there we go. Equals, I want to add together these three angles. So equals, oh, this one's not so easy to create the sum. I need to get that alpha. They changed this thing to make it a lot harder to use. That's too bad. Anyway, if I were to add those things together, it would say 180. And if I drag the points around, the numbers would change, but the 180, would not. If I come over here, desmos.com/geometry. Desmos, math tools, geometry tool. This is a similar sort of thing. I click here on segments. It's basically a ripoff. These are all ripping off an elder program. Anyone old enough to know the Geometer's Sketchpad? Well, the Geometer's Sketchpad was really good. They ripped off something called Cabri. So Cabri came up with this idea of it. It's called dynamic geometry software, and it's really good. Let's see. I haven't messed around with this one so much. Oh, is this not? Here we go. Angle. Choose a point. Oh, cool. Choose a point on a leg. Choose a vertex. Choose a point on the other leg. You go back to select.
Wow.
You can drag the stuff around. Strange though, it doesn't seem to have a really good way of adding the three numbers together to demonstrate that it works. Now, geometry becomes geometry not when it's a bunch of random facts like the three angles in a triangle add up to 180 degrees, but when these things are proved as theorems. Geometry is building up theorems and then using those theorems to prove other theorems. Hold on, I realize my iPad is running low on batteries. Hold on. So how do we go about proving this? Well, we need a starting point. You can't just start proving stuff because if you don't, it's very like philosophical. Like, what do you know? If you're gonna, what do we really know for sure? And for that, at least by the time we get to Euclid, I'm gonna write down Euclid's Elements. He started Euclid's Elements with common notions, and I'll explain with. I'll just pop these up here. There's only 5 of them. So here's Euclid's 5 common notions. Euclid's after Thales, but at least this gives us an idea of the sort of thing they'd be thinking. So they say, okay, things which equal the same thing equal one another, like a transitive property. These things seem totally obvious, of course, but we need some starting point. 2, if equals are added to equals, then the wholes are equal. We do that when we do algebra. If equals are subtracted from equals, the remainders are equal. 4, things that coincide with one another equal one another. So if you have 2 geometric shapes where one's totally on top of the other one, there's nothing sticking out, it's congruent. And 5, the whole is greater than the part. Those don't seem even necessary to say, but that's part of the amazing part of it. They're trying to say stuff that we can all agree on, and you wouldn't argue them, and then they're going to build up geometry from these building blocks. After the common notions, they move on to Euclid's Elements. Whoops. Postulates. And there are 5 of those. Oh, there's a couple of definitions. There's 23 definitions. What does it mean to be parallel? What does it mean to be a diameter? So yes, there's definitions. But then, the 5 postulates. He wants to have as few postulates as possible because this is going to be the building block. Now look at these 5 postulates. Maybe I could zoom in on this a bit. Postulate 1. You could join any 2 points to create a line segment, or you could continue the points to make it as much of the line as you want. So that seems like a good postulate. Like we wouldn't argue that's not true, 2, to produce a finite straight line continuously in a straight line. By this, they just mean that if you have a line segment, you can make it longer. If you have a straight edge, you can make it longer. So very non-controversial. Postulate 3. You can make a circle with any center and radius. So if I give you a point and say, I want this to be the center of the circle, and I say I want the radius of the circle to be equal to 9 inches, you can make a circle like that. Very non-controversial. Postulate 4. All right angles equal one another. Again. Now, how are we going to get from these 4 postulates all the way to the hundreds and hundreds of theorems like Pythagorean theorem, for instance? Because book 1 of Euclid's Elements finishes with proposition 47 and 48, which is Pythagorean theorem and converse of the Pythagorean theorem. How are we going to do that with these somewhat obvious 4 postulates? Well, those 4 postulates, you could do a lot with those 4 postulates and prove a lot of theorems with those 4 postulates. But they had to include a 5th one. And you could tell they didn't want to. Because look at the difference in character between postulates 1, 2, 3, and 4 and postulate 5. that, comma, if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines if produced indefinitely meet on that side on which are the angles less than the two right angles.
What?
So they basically cross paths eventually.
So they are saying, but Scott, you're right. I mean, this is like, huh? How do you have these four beautiful, almost common sense postulates, and then you have this wordy thing that makes no sense on a first read. And so the Greeks were hoping that this didn't have to be a postulate, meaning a thing that we just say, this is our starting point, whether you agree with it or not. They did not want this postulate. They hoped that they could prove this, because they use this as a step in many proofs.
Right.
And without it, they can't do certain proofs. And
So
they couldn't figure out how to prove that postulate to make it a theorem. It's called Euclid's fifth postulate, otherwise known as the parallel postulate. And let me just tell you kind of what they're saying here. So let's call Euclid's fifth postulate, otherwise known as the parallel postulate. It basically says that if you have two parallel lines and you have a transversal, it basically says that these two angles, if they are parallel lines, the two angles are going to add up to 180 degrees. And if the angles don't add up to 180 degrees, 120, 50, that the 120, 50, that the lines will eventually meet. So it basically says, in modern terms, same side interior angles are supplementary. If you have parallel lines and a line that crosses them is called a transversal. That's what Euclid's fifth postulate kind of says. There are consequences of it that are equivalent. For instance, as a result of it, it would also mean that if I have a line and a point, there is only one line that is parallel to the line and passes through that point. In other words, this is the one and only line. There's only one, it's unique, that there's only one line you can make that would be both parallel to the given line and passes through that point. Oh, adjacent. So in a parallelogram, as a consequence, that would mean that in a parallelogram, these adjacent angles, 50, they'd be supplementary. But when I put it in the context of the two parallel lines in the transversal, they're called same side interior angles in that context. But in a parallelogram, you're right, those are called adjacent angles.
Hey, Professor. So why this seems so specific where the other four are so general? Why the need for this particular specific one that they, like you said, they didn't apparently want to write or come up with? What was the problem?
They found that they were unable to prove so many things unless they had this as one of their postulates.
Oh, really?
Namely, you can't prove the Pythagorean theorem without it. I mean, this gets used to prove other theorems, and those theorems get used to prove things like the Pythagorean theorem. So it's really sophisticated when you think that how much torture they must have gone through, and Euclid, whose book is so great, just fell what's the simplest thing I can add as a postulate so that I can build up the geometry from it. Now, thousands of years later, after they tried so hard to prove the fifth postulate, a couple of people in the 1700s said, well, what if it's not true? Oh, by the way, one of the main things that this parallel postulate leads to, and that you couldn't prove without it, is that the sum of the angles of a triangle add up to 180 degrees. So that's how this all started, right? That theorem. He actually could have made that the postulate, that the angles sum of a triangle have to add up to 180 degrees. And from that, you could actually prove the parallel postulate. He had to pick something to be a postulate.
So just to refresh my memory, postulate means, just from ELA, it means to assume something to be true, right?
That's right. That's right. These things are not, we don't prove them. We accept them as true, and hopefully they're not too far-fetched. And in this case, the fifth postulate is pretty far-fetched. So in the 1700s, they examined what would happen if the parallel postulate was not true. And from that, they came up with something called non-Euclidean geometry. And the most dramatic example of it is if your surface isn't a plane, it's on a sphere, and you draw two longitude lines. You would have a triangle. If your triangle's not, if straight lines are defined as these arcs, this triangle would have a angle sum of more than 180 degrees. Of course, the longitude lines are always perpendicular to the equator. So you have two right angles and an angle up here that was not right angle. It could even be a 90-degree angle also, and you could have a 270-degree triangle. So they actually invented something called non-Euclidean geometry by saying, what if the parallel postulate's not true, and we replace it with a different postulate, we get non-Euclidean geometry. Well, non-Euclidean geometry is used in like modern physics to describe like relativity and things like that. So Euclidean geometry is true in an idealized world where everything is on a plane, but it's a great starting point for these other things. Now you might wonder, how do we go about proving that there's 180 degrees in a triangle? So Pythagoras has the proof that we generally use in school. Pythagoras proof goes like this. Actually, I have over here in today's lesson, I have a thing that says History of Math 2022. And when you click on that, it brings this thing up, which has 9 sketches. And you can bring this up on your own computer and follow along that way. Interactive sketches. This is today's lesson. These 9 sketches I'm going to use so you could interact with these. So if I click on Pythagoras sum of angles, go full screen. So what we see here is a triangle, and drawn from the top vertex is a line parallel to the base. And we can make that line because of, postulate, Euclid's fifth postulate said that we can draw a line parallel to another line through a point, and it's a unique line. Pythagoras wouldn't have said it this way. It would have been pretty like common sense that you can draw a parallel line. without calling it a postulate. Now look at what happens. Oh, I need to go back to the whiteboard to show this a little bit more easily. And I like to do geometric proofs by putting actual numbers in. So imagine that this triangle is 50, 70, 60 for the three angles of it. And yes, we can see those add up. Oh, someone's coming. We can see those add up to 180 degrees. Let's say I didn't know that. Let's say I just had a 50 and a 70 degree angle. Step one would be to draw this parallel line. Now remember the transversal, and I mentioned that they would know that these two angles were supplementary. Well, there's also something called vertical angles, meaning if you have like a letter X, if this is 130, that's 130 also. That's because in any line, which is equal to 180 degrees, because a line could be made by making two right angles. So if I make like a letter Y, like that, these two angles will be supplementary. And in this picture, like it's like a letter Z, two parallel lines crossed by a transversal. There are 8 angles formed. And half of them are 50. And half of them, all the obtuse ones, are 130. And all the acute ones are 50. And these have names, like we call this 50 in relation to that 50, we call those alternate interior angles. Kind of like if you see like a letter Z, these two angles are going to be congruent because they're called alternate interior angles. On the other hand, this 50 and this 50, or let me say this 130 and this 130, those remind me of the letter F. And those angles are called corresponding angles, and they're congruent. So I'm just going to write down alternate interior angles. And these two are called corresponding angles. And the 130 and the 130 are called vertical angles. So in your geometry review, we're building up a couple of definitions. Adjacent angles. So do we call, two, like the 130 and the 150, they're adjacent because they share a side like that. So two adjacent angles form what's called a linear pair, meaning they make a nice straight line here. They're supplementary, add up to 180 degrees. Okay, back to here. So I have, because this is 50 degrees, this would also need to be 50 degrees because you see the letter Z, alternate interior angles. And because this is 70 degrees, here I have a backwards Z, which means this is 70 degrees also. Now, here I have, if you have a thing that looks like a Y, those two angles add up to 180 degrees, the two angles. If you have something that looks like a line with a V on top of it, these three angles would have to add up to 180 degrees. And that's what we have here. I'm going to use some color now. Red plus green plus blue. So we can see from up here that those three angles add up to 180 degrees, which means that these three angles have to add up to 180 degrees also. And that's Pythagoras' proof that the sum of the angles in a triangle always add up to 180 degrees. It depended on something, not necessarily Euclid postulate 5, but something like that. I mean, we had to believe that it was true that this angle equals that angle and that this angle equals that angle. If you don't believe that's true, then you can't use that as a step in proving the sum of the angles equals 180 degrees. So what did Pythagoras use as his assumption? You know, maybe his assumption was just that, you know, if you have something that looks like a letter Z, that, and these are parallel, that these two angles are equal. That could be a postulate, you know. It seems pretty reasonable, but Euclid doesn't want to make that postulate. So some assumptions have to be made to prove that angles of a triangle equal 180 degrees. As I said, in a sphere, the angles of a triangle don't add up to 180 degrees. So it's not like something that must be true in all possible worlds. Just in the world where everything's on a flat plane, where the parallel postulate is true, postulate 5. And that's our first big theorem proof for today. The sum of the angles of a triangle equals 180 degrees. Now, in case you're wondering, this is a great proof, right? But I have as my second thing, Euclid, book 1, proposition 32. Notice he has in book 1, it's proposition 32, so he avoids this. He has a picture like this. He has a different auxiliary line. Let's take a look at what that looks like. Euclid.
Professor, what's an auxiliary line?
When you draw in, you have a thing you're trying to prove,
Yeah.
but you draw in more lines, because with more, like this line I drew here is called an auxiliary line. That's any line that you add to a diagram.
Okay.
Now, adding the line does not change. Like if these three triangles add up to 180 degrees after you draw this line, it's also true before you drew the line.
Gotcha.
But without the line, you can't prove it. So an auxiliary line is any extra line you draw into your diagram to help you prove your theorem. And you're allowed to draw all the lines you want. You're permitted to.
Huh, okay.
You know, often drawing extra lines doesn't get you anywhere, you know, and just makes the proof more confusing. But in this one, that's that's got to be the all-time great auxiliary line ever drawn. Now, Euclid's Elements is so famous, right? That back in the day, people like the Bible, you would memorize book 1, proposition 32. You know, you'd memorize that for this theorem. So if you were doing another proof that somehow involved, you know, angles add up to 180 degrees, and you're thinking like statements, reasons, your reason would be, you'd say 132. Everyone would know, oh, that's the theorem in Euclid's Elements that says the angles add up to 180 degrees. It's like the Bible, like chapter and verse. It made it a lot easier, right? Because you didn't have to write down all these words in your proof. You could just write 113 and everyone would know what you were talking about. Nowadays, we have all geometry books that number the things in different orders, and people don't have it memorized anymore. And I don't even have these numbers memorized. The only one, I know 1112, and I know that 147 is Pythagorean theorem. But I don't have the chapter and verse memorized from Euclid's Elements. And maybe they didn't memorize it, they would just look them up, but they would be allowed to use those as reasons in proofs. So Euclid waits all the way until book 1, proposition 32. He tries to avoid using postulate 5. I think he avoids it up until about proposition 20. And then proposition 20, he must use it to continue. And then he builds. So here's how Euclid does it. Here's a triangle. I'll just call this ABC, angle A, B, and C. He extends the line, which you can do because postulate 2 says he's allowed to. And he draws a line parallel to AB, which he can do basically because of postulate 5 eventually. And then he says that this angle, let's use some color, this red angle is congruent to this red angle by corresponding angles. And this blue angle is congruent to this angle because of alternate interior angles. There's like a letter Z here. And this green angle is part of both triangles. I'm sorry, it's part of the triangle and it's part. So of course we can see that, I'll just call this angle 1, 2, and 3. Measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals 180 degrees. But angle 2 is also here, and angle 3 is also there. So the triangle, the sum of the angles in the triangle adds up to 180 degrees. So Euclid's way is similar to Pythagoras' way, except Euclid's auxiliary line is parallel. It's funny because I just should have thought about this, but angle 3 happens to also be over here because of alternate interior angles. So if I just use this angle here, I'm doing Pythagoras proof. And if I use Euclid's corresponding angles, I'm doing Euclid's proof. I don't know why he chooses, one over the other. But now we have established our first proof. And we're talking Thales now, because Thales was aware of a few theorems. So what we've established is sum of angles in a triangle is 180 degrees. Now, another theorem that Thales had was this. Here's a triangle. $50, 70. And the question is, how big is this obtuse angle? I'm going to type it into the chat. How big is that obtuse angle?
No, it's 120.
It is 120.
Yes, 120, yes.
Now, one way to get at the 120 is to say that this angle is supplementary to whatever this angle is. And that angle has to be 60 because the three angles add up to 180, which means that these two angles have to add up to 180 also, so it adds up to 120. Notice, though, that the 120 is 50 plus 70. And with that, we get a very important theorem, which is called the exterior angle theorem. And it says that if you have a triangle, angle 3, 1, and 2, that the measure of angle 3 will be the sum of measure of angle 1 plus measure of angle 2. Now you might say, well, I don't really need that theorem, because if I had this question, yes, I understand one way to do it is do 50 plus 70, but maybe I forgot the theorem. So I could always get the answer to that question by figuring out the 60-degree thing first. Well, yeah, that's true. If that's the question they're asking. If they're just asking find the missing angle, it wouldn't matter if you knew the exterior angle theorem or not. But there are times when we need the exterior angle theorem for another reason, not just to calculate the size of the exterior angle. So let's add that in as our second theorem. Exterior angle is equal to the sum of the two. There's three angles in the triangle, so we call those the two remote interior angles. Not including the one that's supplementary to the angle. So that's what that means. This theorem is going to be used in various very famous proofs. And again, a proof is not, oh, how big is this angle? A proof is proving some other theorem, and this will be one of these steps. So our toolkit is very small right now. Our toolkit has two theorems. Some of the angles in a triangle is 180 degrees, and the exterior angle is the sum of the two remote interior angles. And using this, we are going to get a very surprising theorem, which is going to be our third theorem. And it has a name. It's called Bailly'S Theorem, because Bailly's had a list of only, I think, 5 theorems. That's his Euclid's Elements, 5 theorems total. I honestly think one of the 5 was a diameter cuts a circle into 2 equal pieces. But one of his 5 theorems is called Bailly'S Theorem. It's hard to say it. I think if I come over to Desmos, make a new one. Check this out. I make a segment. More tools. Make a midpoint. Make a circle. Basically, that original line segment was a diameter. Oh, this doesn't zoom in and out. Desmos isn't that good. Here, let me go this way. Segment. Midpoint. Circle with center. There we go. Anyone use GeoGebra like regularly? Like do the math teachers are aware of GeoGebra? You just put into the chat. Math teachers familiar that there's this free web thing called GeoGebra that lets you do stuff like this?
Yeah, I heard of it for online learning, but I never really used it.
Okay, So it's a very powerful thing because you can make these sketches, then you could save them, and then you could have the students interact with them. Check this out. Point. I need a point on an object. I'm not liking this view of it. Let's see what happens. Point. Good. See, I put the point on the circle, and if I move the point around, it stays on the circle. Now I make two segments. And I get a triangle. And I can move point G around. Now, if I measure, I'm just going to measure the angle G. That was lucky. I somehow managed to get that angle to be a perfect 90-degree angle. Let's move G around. Now, the other two angles in the triangles change, but it seems no matter where, oops, let me keep it on the top semicircle just because of the way it measures the angle. No matter where on the circle you put that point, the angle is 90 degrees.
Is that
And
because
that's-
using the diameter as the hypotenuse, I guess?
Yes.
And the diameter will be the hypotenuse.
Ah,
That's right, the diameter, right. If this third side, if this side did not go through the center, that wouldn't be true anymore. So it's not just generally true about a triangle inscribed in a circle, but if the triangle is inscribed in a semicircle, it's going to be a right angle. And that is called Bailly's Theorem. And I'm going to show you the proof of it. Again, this must be the center of the circle. That AB must be a diameter. Bailly's theorem does not claim to be true if it's not diameter as one of the sides of the triangle. It seems like pretty hard to prove that, but our friend, the auxiliary line, is going to come in handy here. Anyone have a suspicion about what the auxiliary line segment, which 2 points might be useful?
The line at C?
Say it again.
The line, an auxiliary line at point C?
Well, C is going to be 1 point on the line. What's going to be the other?
Oh,
Oh. Yes, join C and O, which we are permitted to do. Okay, now check this out. I'm going to call this angle 1 and call this angle 2. Now, Euclid says, well, they would have been aware back then. Let me add it to this list. The base angles of an isosceles triangle are congruent. Euclid proves that. It's really it's actually very early in Euclid's Elements to prove that. It seems kind of obvious to us nowadays because the way I think of isosceles triangle, there's almost like a line of symmetry down the middle, which makes these two angles have to be equal also. but it actually is something that Euclid proves. And the proof is actually pretty hard. It actually has a funny name. Let me just see let me see where it is. Oops, someone's coming in. Here you go, Proposition 5. In isosceles triangles, the angles at the base equal one another. That's very early in Euclid's Elements. Do they say that? So let's add that in as something they would have been aware of in Bailey's time. Check it out. OC, that auxiliary line, is a radius. And all radii of the same circle, by the definition of what a circle is, any point connecting the center to the circumference is going to be a radius. So I don't know how big AO or OB, I don't know how big AO is, but OB is the same thing, and OC is the same thing. Now check this out. I have split my right triangle into two isosceles triangles now. BOC is an isosceles triangle, which means that angle OBC and BCO are congruent. On the other hand, this thing that looks kind of like an equilateral triangle, it's an isosceles triangle because it has two sides congruent. So whatever this angle is here, this angle is the same. And whatever this angle is here, this angle is the same. Anyone see the punchline? The finale now? Take a minute to think about that. I see that, Janela. Angle. So why is angle 1 plus angle 2 90 degrees, do you say?
Yes.
Why? What's the how do you make that conclusion?
I was going to say 1 plus 1 equals the angle COB based on the exterior angle theorem.
We could, yeah. We could use exterior angle theorem. Does that get us to? Yes, I see. You could do that. What would happen next?
Well, then you would know COA, right?
Is what?
Which is a whatever 1 plus 1, 180 minus 1 plus 1. Just.
But we don't know what 1 is yet. Like
right.
What it is. So where's this 90 going to come from? Like we don't know what angle A is or angle B.
Well, the original angle at point C was 90 degrees when you split it one.
No, we don't know that yet. That's what we're trying to prove.
Oh.
So I see. So Sonila, were you saying because we know it's a right angle?
Oh,
1 plus
I
2
get
must be
it.
90?
I get it. So
Yes, Scott?
you use the triangle sum theorem, which we know is all triangles are 180 degrees. And if you take the 180, since angle C is 1 and 2, and the other angles are 1 and 2, 1 and 2 plus 1 and 2 must equal 180. So 1 and 2, since they're congruent to each other, both of them must be 90, because 90 and 90 is a 180.
Yes, exactly.
They're 90 each? 1 and 2 are both 90?
Yeah, because takes the sum of all these angles, all 4 of them must be 180. And since you have 1 and 2 and 1 and 2, if that means they're congruent to each other, you split it in half, they have to be 90.
I see. 1 and 2 added together is 90.
Yes.
That's exactly right. Here it is. 1 plus 1 plus 2 plus 2, which I wrote this way. I grouped it. But that's the same thing as saying 2 angle 1s plus 2 angle 2s together is 180.
Exactly.
Divide everything by 2. A single angle 1 plus a single angle 2 would have to be 90 degrees, which is what angle C is.
Right.
So that's one of the all-time proofs,
Wow.
because it proves something very surprising. That this angle, it wasn't just a coincidence that this became 90 degrees, but it had to be 90 degrees. But look at how it builds on the other theorem that the angle sum of a triangle is 180 degrees. And that built on the alternate interior angles are congruent. And that built on postulate 5 somehow.
Yeah. Wow.
So without postulate 5, you can't prove that triangles have 180 degrees, and you can't prove this theorem either. That's
Can I ask
Bailly's
a
theorem.
question?
Yes.
Was there some kind of like practical reason this came up, like the way there was for some of the like Egyptian and Babylonian stuff? Like, were they doing something with circles and triangles?
So the Greek, and this is, I'm glad you asked that, because, you know, we did Babylonians and Egyptians, and it seemed, you know, kind of primitive what they were doing. But also remember, that was 1,300 years before. So even though this was still BC times, it was over 1,000 years later. And they had built up extreme sophistication. So like Euclid's Elements is like an exercise in like philosophy, you know, like it's not really that it's like so practical, although it is true that in those days, astronomy was quite an important thing. And the geometry was driven by astronomy. So they were like proving, but a lot of these theorems are just more like building up this work. So like this theorem about this interior angle, this angle having to be a right angle, is not very practical in the immediate sense. But eventually, geometry becomes so sophisticated that you can do astronomy with it, and so it was going somewhere. But sometimes I worry that if I don't say it enough, the Greeks were amazing, you know, and the Egyptians and Babylonians, they're amazing also for their time period. So if the Greeks made up the Egyptian math and the Babylonians made up the Greek math, we'd be saying they're incredible, you know, but everyone builds on the previous people. And Pythagoras is known to have gone to Egypt to learn a lot of the stuff that he brought back to Greece. So Egypt was building up their math also. Their math got lost, you know, it disintegrated. What happened to the Greek math? Well, the Greek math disintegrated also. But before it got disintegrated, people from the Arab countries made copies of the Greek in like the year like 200 AD. The Greek stuff was all destroyed. There was some library at Alexandria. The Romans came in, they didn't care about math. They destroyed everything. If not for the Arab countries that made copies of the Greeks, we wouldn't have it, you know, most of it. So there's this line of cultures that builds on the other cultures and make copies and build on their copies. And yes, some of the stuff happened, like the Chinese stuff happened pretty independently of everything else. And they have sophisticated math. The Greeks totally deserve the credit they get for like really bringing math to a higher level than it had been. But that doesn't mean that like the Western world is better than, you know, the Eastern world. So it just so happens the Greeks were in the right place at the right time. They had a lot of money. They had slaves. They had leisure time to think about philosophy and this kind of stuff, and that's what they did with their time.
Well, and you look at the Eastern world developed a lot of the math we know today in the like 1100s, right? Like
Yes,
Baghdad.
so
Yep.
in the Arab worlds, between the year like 300, when the Arab world did it all from 300 to like the year 1200. And only then did the Western world, Fibonacci, went and learned the Arab math, what they had developed. Then he brought it to Europe. And then from 1200 until 1800, the Europeans were really the ones to advance the math. But it's a tag team. It's a relay race. It's a relay race. Sadly, we skip after we do Greek math. We're going to skip all the way from 300 BC to 1500 AD. So we did Middle Eastern, with the Babylonians, but really early. But they have another period of Middle Eastern math that's extremely important. But that's not part of the history of math course. I actually need to learn that math a little bit better, and I should. I mean, in my mind, okay, we did some Middle Eastern math, so they were included, but they were included as this sort of crude math that they had. And I don't want you to think that they didn't have sophisticated math. The Middle East was extremely important for 1,000 years, from 300 AD to 1300 AD. That's where it was all happening.
Well, isn't the word
Back to
algebra actually an Arabic word anyways, isn't it?
So is
yeah.
algorithm. So is a lot of
Al-Khwarizmi was a mathematician in around 800 AD. And this is good to mention. I think before I do the European math, I'll in a few days I will. Algorithm is from Al-Khwarizmi, and algebra is from an Arabic word that basically means balancing. So Arab culture is very important. We included it as Babylonian math. That's Iraq now, that area, but they did a lot of really sophisticated math also. Okay, we now have 4 theorems for Bailly's theorem. Bailly's theorem says that
I thought this was number 3, Professor. Didn't you say it was number 3?
I threw in the base angles of
Oh.
an isosceles triangle congruent because we needed it
Okay.
for. I slipped in 3 just because we needed it as a proof for 4.
Yep.
So Bailly's theorem says that this will always be a right angle. Okay, I want to do a break now because that was intense. I hope that you guys are following along with it. People don't have their screens on generally, so I worry that people just kind of have this kind of sort of in the background. But like for me, it's like an intense experience. Like when I'm done with this class, I'm like exhausted. I remember when they offered me going to teach. Some years I teach it, some years I don't. I remember thinking, well, it's 3 hours a day, and then I'll go work out or something. But actually, I'm really tired when this class is done, so I don't go and work out. So, getting paid to do this class, and I like it a lot. Okay, so 10 minutes. See you then.
Sounds good. Thanks.
Okay, hey everybody, welcome back. Yes, someone mentioned, so you can buy Euclid's Elements. When you buy Euclid's Elements, the thing to buy Let's go to Amazon. It's called the 13 Books of Euclid's Elements, but it's made in three volumes. Usually you buy the Dover Classics. I'll show you what that looks like. It's really good. So they have, where is it? No, you don't want that. You want, here it is. So you buy the Dover Classics. Volume 1 is books 1 and 2. And then volume 2, here's all 3 together. So for $50, you buy these 3 books. Because if you buy it all in one giant book, it's just so big. These books have a lot of the commentary also. In the 1800s, somebody made a visual version of it. Where is it? Oh, here. So you can buy a single, one copy here, Oliver Burns' Elements. This is pretty cool, although, oh, they're selling that for $9.99. That's pretty cool. That's done with like colors and like pictures and stuff. It's beautiful, but it's not easy to follow what's going on in the Burns book. But you got to admit, these pictures are compelling with all the color in them. I would recommend, if you really want to own it, buy for $50 the 3 volume set that look like this. Now, for completely free, you could type in Euclid's Elements online, and you'll get definitive this one. Professor Joyce. Let me put this into the chat. So what this is he made the entire Euclid's Elements, you know, book 1. Oh wait, did I lose? Yep, I did lose. Hold on. All the different propositions. You know, you click on one. The only thing about this, and it's pretty cool, like it has all the pictures and everything, but they're not interactive in that you can't like move them around. But it's basically an entire Euclid's Elements that you could study. Pretty cool. Of course, there's no copyright on Euclid's Elements written in 300 BC. Let me come over here. I need to reattach. Hold on. 084. Sorry, hold on. 084461. Okay, so now that we've done Thales, it's time to look at propositions from Euclid's Elements themselves. And if I come over here, you can see that after the common notions and the 5 postulates, including the dreaded postulate 5, we have the propositions. There are about 400 propositions. Some of them are theorems, like Pythagorean theorem, proof that vertical angles are congruent, things like that. And some of them are constructions. I would say about a quarter of them are constructions using a compass and a straight edge, and 3/4 of them are theorems. But the theorems, the constructions is the purpose of Euclid's Elements. He basically shows how to use a compass and a straight edge to produce various shapes. And then he proves theorems so that you can show that the construction actually accomplished what it claimed to. And the very first thing, book 1, proposition 1 is, how could you use a compass and a straight edge to create a perfect equilateral triangle? So let's just make a note here. Oh, I don't think I want that yet. There you go. Book 1, proposition 1, how to make an equilateral triangle. Now, the construction tools are 2 things: a compass and a straight edge. A straight edge does not mean the same thing as a ruler. A straight edge is literally like a ruler, but with no markings on it. And it allows us to make straight lines, which, according to the common notions and the postulates, we can make straight lines. Now, a compass is actually not what you think of. When you picture a compass, you picture this thing, pen, pencil, and a point here. Their compass was what's called a collapsible compass, which means that when you lift it, it snaps back into place, which makes it much harder to use. Because sometimes you have like a line segment and you want to make a copy of the line segment over here, and you kind of open the compass up, and then you use the compass as a way to transfer one line segment to make a copy of it. If you have a collapsible compass, you lift up the compass, it collapses, you can't do that. You might say, well, why did they restrict themselves? Is it that they didn't have the technology to make a compass that stays open? Did they not have the technology to make a ruler that has markings on it? And the answer is they did have the technology. They had all kinds of tools. They had something called a flexible ruler. They had compasses that were not collapsible. But since this geometry was like a very theoretical thing for them, they wanted to see, what can I do with the 2 most simple tools possible? Something that makes lines, something that makes circles. And they self-imposed this restriction of only being able to use a compass, collapsible compass, and a straight edge. So book 1, proposition 1 is how to make an equilateral triangle. And for this is real fun. I have in here, you click on history of math and you get to here. And we have 1, 2, 3, 4, 5 constructions. And then we're going to be done for today. We might be done a little bit early today because the other thing be too hard to start. This course used to be 2 hours a day. So I find that I'm having a lot of time to fill, actually. And I don't have to rush at all through the material. So if you want to bring this up in another window, now this sketch is kind of cool because what I have here is a line segment that you can move around. But on the top, I have tools. And I only have 3 tools: a straight edge tool, a circle tool, compass, collapsible compass. This arrow lets me move stuff around, zoom in, zoom out. Oh, point and intersect, I'll explain what that means. Line and segment, circle. So there's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things I could do. the goal is to use this limited set of tools to create a perfect equilateral triangle where AB is one of the sides. And the way we do that is it takes 3 steps. Step 1, make a circle that has A as the center and that passes through point B. Step 2, make a circle with B as the center that passes through A. Step 3, mark the intersection of the 2 circles. There's actually 2 intersections, but let's just do the one that's up here. Step 4 and 5, connect A to C, connect B to C. And Euclid says, this is an equilateral triangle. Will you take a few minutes now to think about how does he justify that it's an equilateral triangle? Go ahead, take a few minutes to ponder that. How do we know that he's right? Okay, think about that for a few minutes, and then we'll talk about it. Okay, somebody want to volunteer to explain? You could raise your hand in the chat, and I'll see who raises their hand. Why? How can we be so sure that this it's certainly a triangle, but who's to say that it is a perfect equilateral triangle? Someone volunteer. Some people put it into the chat, I saw. Okay, Tina, you want to give an explanation? How do we know that this really is equilateral triangle and not just it kind of looks like one?
If the blue dots are centers of the circle, that
That's right.
means that the legs of the sides of the triangle are radii. So if they're all radii, they're all the same distance
That's right.
to the
They're
circumference.
all radii. And who's to say the 2 circles are the same size? Because there's a small circle and a big circle, it wouldn't work. So how do we know that the circles are actually the same size circle?
Because A being the center of the circle A reaches out to the intersection B. And B being the center of the circle B reaches out to the intersection A. And so therefore
Okay.
AB, same line, so both circles are equal.
That's right. Okay, check it out. Euclid's Elements. Now, since the point A is the center of circle CDB, therefore AC equals AB. Again, since point B is the center of circle CAE, therefore BC equals BA. But AC was proved equal to AB, therefore each of the straight lines AC and AB equals AB. And things which equal the same thing also equal one another, common notion 1. Therefore, the 3 straight lines are equal to one another. Therefore, a triangle ABC is equilateral by definition. And you see, he justifies each of the steps. Postulate 3, postulate 1, definition 15, common notion 1, definition 20. QED means it's been proved. QEF, I've never seen that before with an F. And then this guy does a whole, all this stuff to say about it, because he's like, some people have argued, how do you know the two circles intersect even? Euclid assumed that. But this guy in the guide explains, like, why does point C exist? Why is it a plane figure? Why does it contain equal, you could do all kinds of analysis of this. Okay, well, that's book one, proposition one. Now, you might wonder, why does he start with that? Well, there's two reasons. It's the one thing he can construct, and eventually he constructs more and more complicated things. Oh, let me see, there's something going on in the chat. Oh, quod erat facendium, that which was to be done. Cool. Oh yeah, Euclidia. There's a iPhone app where you have to do constructions. It's really cool, except at some point it gets so hard really quickly, and then you have to pay money to get hints, or it doesn't let you continue. But I was having really a lot of fun with it until it got too hard for me, which was fast. Like I did like 20 challenges. Oh, someone mentioned about South America. No, all I know, the Mayans had this great calendar and they had a base 20 system, but I don't know much about their math. So that hasn't been widely studied. So not only does Euclid ultimately create more complicated things, like tomorrow or Monday, we get to see how to construct pentagon, which is very hard. Square is very easy. Hexagon is actually very easy. So 3, 4, and 6 are easy. 5 sides is very hard. And 7 sides, impossible. So it just shows you have a quick range of easy polygons, but they do even more complicated things. But one of the reasons that they do this first is because book 1, proposition 2, which I'm not going to teach you, but I'm just going to mention. Book 1, proposition 2 is about how you can copy a straight line, a line segment, to another location with a collapsible compass. If we use a regular compass, you just lift it up. You can copy a line segment. But with a collapsible compass, it's an entire process, and that process involves an equilateral triangle. And once you prove that you can copy a line segment to another location with a collapsible compass, you then, from then on, are permitted to use the regular kind of compass. So book 1, proposition 2 lets us say, okay, yes, we're only really allowed to use a collapsible compass, but this shows that collapsible compass can be used to transfer line segments, so I will let you use a regular compass from now on. So that's how they get out of the collapsible compass issue, because otherwise it would take like 15 minutes to copy a line segment anytime you needed to. Okay, we only have 4 more constructions. And these are fun for you to do. You can just go to them and you can, reset. Does it have a reset button? This one, no, this one doesn't. It should though. I should have made it have a reset button so you could practice the steps of the construction. It would be a good question on the final exam, like do this construction, do that construction, not with, maybe we bring in a compass and a straight edge. I don't know. I got to think about it. I might just have us do it by freehand. Okay, the next construction, which is, hold on, let me look at what number it was. It's book 1, proposition 10, which is how to use a compass and a straight edge to construct the midpoint and the perpendicular bisector of a line segment. Now I have a new tool here, and I'm sorry that, see this triangle here? That's actually supposed to be equilateral triangle, because what that tool does, we can just use it to make equilateral triangles that we want. Because that's what geometry is. You get a tool, you learn how to make equilateral triangle, and it's kind of like now that I can make an equilateral triangle anytime I want, in my thing here, I add that as a tool. What's that? Angle bisector. I better do 1,9 first then. Okay, let's do this one first. Angle bisector. This is book 1, proposition 9. Oh, I see. I have it in the wrong order here. Book 1, proposition 9 is angle bisector. Now you might wonder what happens in between proposition 2 and proposition 9. Well, there's a very important proposition that I'm just going to mention. It really is a postulate disguised as a proposition, and it's extremely important. It's proposition 8, which comes from proposition 4. So I got to talk about these because this is extremely important. Proposition 1,4 and 1,8. This is very important. If you haven't taken geometry in a while, listen carefully. Two triangles are congruent. Imagine I measured.
Are you drawing something? Because we're still on the propositions.
Oh, thanks. Here's two triangles. What I'm drawing here probably can't actually make a triangle of these sides, but this is to make a point here. So here's two triangles. Every triangle has 3 sides and 3 angles. And for sure, if I want to be like bet my life that the 2 triangles are congruent, it would require measuring all 6 of these things. The 3 sides and the 3 angles. And then in the other triangle, I'd measure the same corresponding pieces. Well, I don't know why I wrote 37 there. And if all 6 match up, we are sure they are congruent. It means if I put this triangle and slid it on top of this one, it would coincide exactly with it. And one of Euclid's common notions or whatever was that things that coincide are equal. Now, what book 1 proposition 4 says is that I don't need to measure all 6 things. Book 1 proposition 4 says that if I have 2 triangles, I will use my same numbers, 10, 45, 5. That I don't need to measure all 6 of the things. If I just knew any 2 sides were equal, and that the angle that happens to be between those 2 sides was equal to the angle that was between the 2 sides, corresponding sides in the other triangle, that I can now say, yes, the triangles are congruent. And this is called, in math, the side angle side postulate. otherwise known as SAS. You might be, if you haven't studied geometry in many years, if you're one of the math teachers, you've been doing mostly algebra type stuff, that's what SAS means. And once you know that, once you know the two sides and the angle between are equal to two sides and the angle between on another, you can then go ahead and say as a conclusion, so first I could say they're congruent by SAS. And after you say that, you can then say, well, that also means that the other three things are equal also. So I can conclude that this is 12 and this is 80 and this is, and that's by using something called corresponding parts.
I think Sonia pointed out you're missing about 20 degrees in your triangle.
Oh no, thanks. Let's make this 100. Thanks. Corresponding parts of congruent triangles are congruent, which a lot of math teachers abbreviate to CPCTC. So CPCTC, corresponding parts of congruent triangles are congruent, are after you've proved that the two triangles are congruent because you got these three pieces, you can then talk about the other three pieces. So SAS is my way of saying, okay, because I've checked the three sides, two sides and an angle between them were equal to two sides and an angle between them in the other triangle, I now know they're congruent by 1/4. And then corresponding parts of congruent triangles are congruent allows me to conclude about the other three pieces that weren't mentioned in the SAS. Now it's listed as a proposition in Euclid's Elements. It's proposition it's proposition 7, but it's not. It's postulate. He doesn't prove it. What does he say? He does some kind of indirect proof. I don't know. It's not. This isn't a good proof. Let me look at it. Let two others, if possible, given two straight lines and meeting in a point that cannot be constructed. Given two straight lines, wait, that's proposition 7. The wrong proposition.
I thought it was proposition 4 you were talking about, wasn't it?
Yeah, proposition 4. Yeah, if two triangles have two sides equal to two sides respectively and have the angles contained by their equal straight lines equal, then they also have, oh, it's funny. He doesn't just say they're congruent. He then jumps to the CPTC piece. He says, then they also have base equal to base, the triangle equals the triangle, and the remaining angles, angles respectively, namely opposite the equal sides. So what's kind of cool is that they could jump straight to 1/4. So if they were like this,
We can't see what you're drawing.
oh, thanks. So if AC is congruent to DF given, and AB is congruent to a DE, sorry, given, and angle A is congruent to angle D given, we would say ACB, triangle ACB is congruent to triangle DEF by side angle side, and then say angle B is congruent to angle E by CPCTC. That's what we would do. But they would be able to just not say this And they would just say as their answer. Reason 1-4. If we have two sides and an angle between them, we can then say what we want about the other angles and the other side. Now 1-8. 1-8 says if two sides equal, if all three sides are equal, then the triangles are equal. So what 1-8 is saying, if I come back to here, I'll just go like that. I'll make a new one. One eight is saying these triangles are congruent by what's called side, side, side. That's actually a theorem because they use the side angle side as a step in proving it. But you have to make a postulate about one of those side, 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 side angle side. He cheated a bit. He probably should have made a sixth postulate for the side angle side, but that's okay. It's really hard to, by his logic, it's okay to, he does do a bit of an argument about, oh, I never looked at it. I'm just curious. Let's see. Here are the two triangles. I say, it's written in the first person, base BC also equals and equals equals, and why? If triangle ABC is superimposed on triangle DEF, and if A is placed on D, and AB on ADE, then the point B is also coincides. You see, that's not a proof. If we put them on top of each other, they would be congruent, obviously, he says. I wonder what he says here. I think there's a lot to say about this, whether you're allowed to just superimpose stuff on top of other stuff as part of your proof. It wasn't one of his postulates or common notions. But proposition 8 does utilize proposition 4 as its as one of its main. See, proposition 8 uses proposition. Oh, it uses 1-7. What was 1-7? 1-7. If two straight lines meeting in a point exactly straight from the same straight line and the same side of two other straight lines. Well, this uses 1-5. What's 1-5? Oh, isosceles triangle. Okay. The isosceles triangle proof uses 1-4, the SAS thing. And then 1-5 is used in something that helps us prove 1-8. Proposition 5, proving that the isosceles triangles are equal, is actually very hard. And back then, this proposition 5 was called the bridge of asses. Ass meaning like the donkey, because you had to be smart enough to, wait, they mentioned it here. Wait, oh, they don't say it? Yeah, this proposition has called Pons Asinorum, or ass's bridge. Whether this name is due to the difficulty or the resemblance of the figure to a bridge is not clear. Very few of the propositions in Euclid's Elements are known by names. I think they said it was hard to cross to do this, so it was like a bridge that the mule wouldn't be able to do this proof.
So I4 is SAS and I8 is SSS?
That's right. And that's all we need to know now. I'm just riffing on a couple of things, but yes, 1-4 is SAS and 1-8 is SSS. Whoops. Okay, let's move on to our next construction now. This is construction 1-9, which is done right after 1/8. And that's because it is going to use SSS. Let's see how it works. Angle bisector. Okay, watch carefully, and you could do this along with me if you want. You can change the angle that you want to bisect. Oh, make sure am I on the right? Yeah. These 2 points, B and C, they're not using the construction. They're just so that you'd be able to change the angle to just make sure, you know, this thing still works. Okay, step 1. Make a circle that has A as its center and pick any point you want on either of the lines to be so you can get the radius of the circle. We could have started this one. Maybe it's even better. Oh, this one has a refresh. So if you push this icon, it refreshes it. I like to do this. Point on object. Whoops, that's not point on object. Undo. I like to go point on object and then just put a point anywhere on the ray. Then I go circle with center and through point and move the point till it clicks to that point. Then go to intersect and label the intersection of the circle with the other ray. And now, sorry that this icon is distorted. I made it. This icon is the equilateral triangle maker. Book 1, proposition 1. Click on G and H, and it will make an equilateral triangle, which of course we could do with equilateral triangle step, but we don't need to. And then finally, if you click here, you can go to ray. You know what? I'll just make it a line segment. You can make a ray if you want, or and Euclid contends that the angle's been bisected. If you don't believe it, come to this tool. And I think you have to click I, A, G, 14, and then H, A, I. And as you can see, it worked. And then to have fun, you can come here and move. I love doing this. Move C and B around and watch it show what the construction would look like with a different angle. Don't move C below B.
Very cool. Very, very cool.
So now the question is, why does this work? Where's the okay, there's the picture. Oh, I drew in like too much because I have the entire construction with the equilateral triangles constructed. Anyone know why this can you hear? Let's stick some letters on here. O, A, B, C. Can you prove informally that angle AOC is congruent to angle EOC? Okay, what's the gist of that proof? Anyone want to say it in the chat?
I was just going to say, well, we know that angle B equals angle A equals angle C, right? Because it's an equilateral triangle.
Equilateral triangle, yes.
So therefore, BCO and OCA are bisected with that line because we
Don't know
created
that.
We
You,
don't
you
know
could
that.
cut it. You could cut it into two pieces that aren't equal to each other. So we don't know for sure that BCO and that BCO and ACO are congruent.
Oh, wait, I see it. Isn't it the SAS theorem? Or
Which
posture?
angle?
So we know OB is congruent to OA because they're both radii, right? We
That's
know
true.
the angle is bisected.
We
So
don't know that.
oh, we
That's what
don't.
we're trying to prove.
Oh, because I was going to say OC is also congruent to each other, right?
OC, very nice. OC is
It's-
part of its own. OC is equal to itself. So
Right.
I'm gonna here's modern.
Yes, it's
OB is congruent into OA, radii of same circle.
Yeah.
OC is congruent to itself.
Uh-huh.
Reflexive property. I like to make an X here to show that.
Yeah. Okay.
But we don't know about the angle because that's the thing we're trying to prove. So what's
Okay.
the next step?
Can we do side, side, side? Because BC and CA have the same length?
That's right. BC is congruent to CA because it was made as part of an equilateral triangle.
Ah, so that's why I8 is SSS, because you need that for this.
That's right. Triangle OBC is congruent to triangle OAC by SSS. This line, can I get rid of that line now? Let me erase, if I can erase this tiny line. That line kind of gets in the way. In fact, this arc gets in the way also. So I'm just going to erase that for now. So think of how often, if you're teaching geometry, you see a thing like this. Prove that angle 1 is congruent to angle 2. And the steps are reflexive, SSS, CPCTC. Of course, Euclid would not say this, and he would just say 1, 1, 8. 1, 8. Jump straight to, I got the 3 pieces, side, side, side. So I could jump straight to saying the other 3 pieces or one of the other 3 pieces is equal also. Now, to me, this is like kind of fun. See, Euclid's Elements is a book of constructions, and the theorems are just so he teaches you a theorem because he's going to need it to prove the next construction worked. Sadly, geometry now, ever since, I don't know, at least the 1960s, constructions, if you teach geometry, constructions is a topic you throw in the last week of school. The last week of school, you break out the compass and straight edge and learn how to do some constructions. But for Euclid, it's the first thing he does, and the theorems all support the next construction. So he needs SSS so that he can prove that you can construct an angle bisector. So Euclid's Elements has like a narrative to it, like a spy movie, where you get like the piece of information from the guy right before he dies, and then that gives you the clue you need. Euclid's Elements has like suspense. Like, why am I learning this crazy SSS theorem? We need it for the next construction. So I thought it would be really fun to teach a geometry course where I do it with constructions and the theorems become a vehicle. Because otherwise, what is it? You learn SSS. Why? Why do you learn SSS? Big deal. Now I can solve this question, that I couldn't solve before. But who cares about this question? There's 2 sides and and I want to know if these 2 angles are equal. But if you're doing a construction, there's some motivation for learning SSS, because it's going to help me prove that this construction works. Okay, let's move on. There's only 3 more. The next one is book 1, proposition 10. I had these in the wrong order. Okay, book 1, proposition 10 is perpendicular bisector / midpoint of a line segment. And the reason it's 10 is because as one of its steps, it's going to use angle bisector, proposition 9. And that's why. And I'm so proud. I made all these things in GeoGebra, like limited toolkits and things. It was really hard. So here it is. Here's that construction. First, I'll show you the steps, and then we'll analyze why it works. Step 1, make an equilateral triangle on the line segment. Step 2, make angle bisector, which you do by clicking on the vertex. Second. Step 3, find where the angle bisector intersects side. Step 4, measure AG. And measure GB.
So I have a question for you. You keep hitting the measurement to prove they're congruent, but if these people are in BC with no measurements on the straight edge, how are they doing what you're doing?
Oh, well, this is just to show you that it's working. But no, they're going to prove it.
Okay.
They're going to do a proof, right? That proof that we just did before of the angle bisector theorem.
Yep.
That proof, the SAS, this thing, that proves it without any measurement.
Okay.
This proves that the angles are congruent, that it's bisected without any measurement. Of course, measuring could be inaccurate, but a geometric proof, it can't be. So I'm measuring it just to show you that it certainly seems to be equal.
Right.
But that doesn't prove it. Even if this was exactly accurate, it doesn't prove that it's always true. If I change it, maybe there's some case where it wouldn't.
Okay.
So now let's do proof. That's funny. So I'm improving this lesson actually, because that was that, and so here was the construction. So given ABC is equilateral and CD is angle bisector, prove that AD is congruent to DB, which makes D a midpoint. Okay, they don't want to say what's the deal with this one? What's going to be the key proposition that gets used to prove that AD is congruent to DB, which would make D the midpoint?
This would be the SAS?
Yes. SAS. This side equals this side equals this side, but it doesn't matter, that third one. So that's the side. The A comes from the angle bisector. And the third side is the shared side the reflexive side. So the reason would be 1, 4. Now it's also true by 1, 4 that this angle and this angle would have to be equal also. But those angles are equal and they add up to 180 degrees, so they would both be right angles. Which makes this not just the midpoints, but it makes the CD the perpendicular bisector. So this construction gets us the perpendicular bisector and the midpoint. And that's a very important construction, 110. Perpendicular bisector and midpoint. It relied on 1, 9, which had the angle bisector. 1, 9 relied on 1, 8, side, side, side. Side, side, side relied on 1, 4, side angle side. Side angle side was really a postulate, not a postulate, not a proposition, because he didn't really prove it. So there's this chain of building stuff. Okay. We're only going to do one more today. I'm going to save. I'm going to save this one for next time. So the last construction for today. The last construction is how you can. So we can make a midpoint. But what if we want to divide a line into 3 equal pieces or 5 equal? 4 pieces isn't bad. I could just do midpoints all around. What if I want to divide a line segment up into 5 pieces or 3 pieces or 7 pieces? That's actually possible. Crazy thing about this is actually not done until, get this, book 6, proposition 9. You might say, why am I jumping ahead to that? I'm jumping ahead to it because it's a pretty easy construction, but I'll tell you why it's so late in Euclid's Elements. Okay, let me show you how this one works. Step 1. I'm gonna divide this into three equal pieces, but I could do this with more pieces. I can cut it into 7 equal pieces, 9 equal pieces, whatever number of equal pieces I want. Step 1, come over here. Actually, come over here. Make a ray from B. Just go out. It doesn't matter where this point is. I'm going to make it over here. Just doesn't matter where. I'll make it over here. It doesn't matter. That point C is just, I don't even want to see that point C. It's gonna, but I could use point C to move, change this angle. Okay, step 2. Take a point on object, and put it somewhere around here. It really could go anywhere, but you'll see why we don't want to make it too far up on the line. That point could go anywhere you want on that ray. Next step, make a circle, and I'm recording all this, that has D as the center and goes through B. Now, find the other intersection points of the circle with that line. And now make one more circle. This one has E as the center and goes through D. And now I'll make a point here. Okay, I don't have to make any more circles. Notice how DB, ED, and FE are all congruent to each other. So for whatever it's worth, oops. BF is cut into 3 equal pieces. If I wanted to make it 4 equal pieces, I'd make another circle. Well, that's just great. Except I don't want to cut BF. No one asked about BF being cut into 3 equal pieces. They wanted AB cut into 3 equal pieces. So here comes the sneaky trick. Join F to A. Okay, I forgot to mention. I'm not going to show you this construction. I'm going to show you this, but there's something I forgot to tell you. Sorry, let's pause that for a sec. I forgot to tell you that book 1, I need, hold on. We're not going to prove this one. I'm just going to tell you that it is possible. Hold on. Book 1, proposition 31. Let's just, for reference, that it's possible to use a compass and a straight edge to make a parallel line. Sorry, I didn't mention that before. Let me just mention it now. Book 1, proposition 31 teaches how to construct a line parallel to a given line through a given point. Okay, that's a thing, okay? We're not going to do that one. Let's just say it's possible. So I'll let you just kind of, you can do it. I'll permit you. No construction. Because I'm telling you that it is possible and that he did show how to do it, we'll just assume that yes, I'm not lying. So here I have a tool that's a parallel line tool. When I click on that, I can click on a line and then on a point, and it will make a line parallel to the line through that point. And I'm going to make another line. So I made these 2 parallel lines. And now I get these 2 intersection points where those parallel lines hit the triangle. And just to check, if I measure this, and I measure this, and I measure this, they all do. It's a trisect the line segment. And remember I said C could be wherever. See, if I change C, I get the same picture. And what I call D, doesn't matter how big those are either. So you could divide a line segment into whatever number of sides, number of pieces that you want. The question is, why does this work? That'll be our last question for today. And I'll just make it a thing that someone could say it, unmute and say it, or chat or something. Why does this construction work? We know that this piece equals this piece equals this piece, and that this is parallel to this is parallel to that. Why does it work? How is this enough information to be sure that this equals that equals that? There's a 2-word explanation. And it's not going to be using like a side angle side or ASA. Anyone have a thought about how I can be sure that these 3 sides must be equal? Well, there are a lot of corresponding angles. That's true. This angle equals that angle equals that angle. That's true. That is relevant. Witchcraft. 2 words. See, corresponding angles was a good idea. But why? What do we do with corresponding angles? Yes. Judette says similar triangles. There are 3 triangles in this picture. A small one, a medium one, and a large one. And when I put those triangles side by side, we would have, I'll say x, 2x, 3x. And yes, the corresponding angles, we don't really need the corresponding angles because they all share this angle over here. Oh no, we do need the corresponding angles because that's what makes it similar triangles. So they're similar triangles because they share 2 angles. If they share 2 angles, they must share the 3rd angle also because they all have to add up to 180. But this small triangle's corresponding side, or this medium one, is double the length, and this bigger one is triple the length. So if this is y, 2y, 3y, this would be 2y, which would make this piece y, and this would be 3y, which would make that piece y.
Wait, can you go back to the sharing of the angles? I see all 3 triangles sharing only one angle. I don't see them sharing.
That angle there? Yes.
Yeah.
So there's also this angle, and that angle. Because these are parallel lines, and this is the transversal.
Oh, right. They're equal.
Those are all corresponding angles. So these are similar triangles, all 3 of them. If you have 2 angles the same, then your 3rd angle must be the same also, and the triangles will be similar. So the medium one is just a small one that's doubled in size, and the big one is tripled in size. Okay, so is that clear? Remember the letter F? When back in the beginning of the class, I showed you how if you have a transversal, if you have 2 lines and a transversal, this angle will equal that angle. Well, that happens right here and here. And while we're at it, in this case, there's actually 3 parallel lines cut by a transversal. So this angle equals this angle equals that angle. So similar triangles. Now you might wonder, why is this book 6 proposition 9? And the answer is, just like Euclid tried to avoid using postulate 5 as long as he could, they also were a little suspicious of similar triangles. I'll tell you about why that is another time. So they tried to do all the proofs they could do that did not rely on similar triangles first. But they couldn't figure out a way to prove this without similar triangles. So they broke down and they explained similar triangles. They wanted to do all of geometry with no similar triangles. And they actually managed to do a lot of proofs that we nowadays use similar triangles for, and they managed to avoid them. But this had to wait till book 6, proposition 9. Nowadays, we probably could introduce similar triangles right away and do this proof in book 1, or much earlier in the progression. Okay, I am not going to do the last one today. On Monday we have. So for homework, you will there's an assignment, but I think there's one question you can't do now because I hadn't done that last question. let me just make sure. Actually, there's 2 questions we can't do. I'm gonna get rid of those. What you should do though is study. Oh, hold on. I don't think we could do question 2 either. Rats. Hold on. Let me just see if I got to see what this shows. Okay, so it looks like I see. Okay, so all we could do is question 1. We can't do 2 and 3 because that was based on the next one. We can't do 4. Okay, but we can do 5, 6. We can't do 7. We can't do 8. Okay, I am going to make up. Your homework is to be able to do these 1, 2, 3, 4, these constructions. 1, 2, 3, 4. That you know the steps for those constructions and that you're aware of the theorems that I mentioned already today. So I'm going to make up like a different assignment, but I'm going away in 15 minutes. So I'll post something. I'll post something for you, a different homework assignment, because this one is not. I didn't use my time well, so I'm just going to say stay tuned.
Professor, can we use the project as the homework?
The project, that's not due till before the final.
Oh, I thought I saw the 25th. I thought it was Monday.
Oh no, a week from Monday. I need to change that. It says that. Mainly study what we did today. Make sure you know proofs of Bailly's and sum of angles of a triangle, and you know which theorems Euclid used in the 4 constructions: equilateral triangle, angle bisector, perpendicular bisector / midpoint, and divide segment into n equal pieces.
Hi, can I call you back?
Yes. Oh, so that's going to be it for today. Sorry that teacher's supposed to look at the assignment and make sure they cover all the things in there, but I ran out of time, and that's okay. I'm not in a rush. I just need to change this assignment. For now, if you could do these 4 constructions on your own, you know, you go to the blank piece, the blank page, and try to do these 4. And if you understand the proofs of the 4 constructions, you're in good shape. But I'm going to make something. Okay, so I'll stick around for a few seconds now.
Professor, will you post the recording for today?
And the notes?
Yes. So let me stop